Well, welcome back to our class on algorithms and data structures. We just finished up going through dictionaries and as well as hashing and showing how hashing can be used as a dictionary implementation to make it more efficient. And there's some things that you have to be dealing with to make that all happen. And so some interesting material. Now we're going to be getting into a new area where we'll be talking about trees and tree implementation. So first, let's talk about trees. So that'll be the focus of this lecture. So here is the table of contents. And so we'll be talking about tree concepts, ways of traversing a tree, the Java interfaces for trees. Then we'll talk about binary trees, give some examples, and then examples of the general trees. As a plant, a tree is well known as a way to organize data. The tree is more familiar than you might think. Family tree or a chart of players in a tournament are two common examples of a tree. A tree provides a hierarchical structure in which data items have the ancestors and descendants. The organization is richer and more varied than any you have seen previously. So this chapter explores the ADT tree in its two forms, binary and general, and provides several examples of how such trees are used. So let's get into tree concepts. The tree organizations that you have seen so far have placed data in a linear order. Objects in a stack, queue, list, or dictionary appear one after the other. As useful as these organizations are, you often must categorize data into groups and subgroups. Such a classification is hierarchical or nonlinear, since the data items appear at various levels within the organization. We begin by looking at several familiar examples of hierarchical data. Each example will be illustrated by a diagram that represents a tree. So here's an example of a family tree, and so your relatives can be arranged hierarchically more than one way. So figure 24.1 shows Carol's children, grandchildren. Her son Brett has one daughter, Susan, Carol's daughter. Jennifer has two children, Jared and Jamie. And so that's all listed here. Using a different arrangement, figure 24.2 shows Jared's parents and grandparents. Jared's father is John and his mother is Jennifer. John's father and mother are James and Mary. Jennifer's parents are Robert and Carol. Here's an example of a university's organizations. So corporations, schools, churches, and governments all organize their staff in a hierarchical fashion. For example, in 24.3, it shows a portion of an administrative structure of a typical university. All offices ultimately report to the president. Immediately beneath the president are three vice presidents. The vice presidents for academic affairs, for example, oversees the deans of the colleges. The deans in turn supervise the chairs of the various academic departments, such as computer science and accounting. Here's an example of a file directory. Typically, you organize the files on your computer into folders or directories. Each folder contains several other folders and or files. Figure 24.4 shows the organization of the folders and files on Paul's computer. The organization is hierarchical. That is, all of Paul's files are organized within folders that are ultimately within the folder My Stuff. For example, to look at his budget, Paul would start with the folder My Stuff, find the folder Home, then finally locate the budget.txt file. For tree terminology, each of the previous figures is an example of a tree. A tree is a set of nodes connected by edges that indicate the relationship among the nodes. The nodes are arranged in levels that indicate the node's hierarchy. At the top level is a single node called the root. Figure 24.5 shows a tree that is that, except for the names of the nodes, is identical to the tree in 24.4. In figure 24.4, the root of the tree is the folder My Stuff. Figure 24.5, the root is node A. The nodes at each successive level of a tree are the children of the nodes at the present level. A node that has children is the parents of those children. In figure 24.5, node A is the parents of node B, C, D, and E. Since these children have the same parents, they are called siblings. They also are the descendants of node A, and and node A is their ancestor. Furthermore, node P is a descendant of A, and A is an ancestor of P. Notice that node P has no children. Such a node is called a leaf. A node that is not a leaf, that is one that has children, is called either an interior node or a non-leaf. Such a node is also a parent. Something to note, while the roots of most plants are firmly in the ground, the roots of an ADT tree is in the tree's top. It is the origin of the hierarchical organization. Each node can have children. A node with children is a parent, a node without children is a leaf. The root is the only node that has no parent. All other nodes have one parent each. So let's talk about binary trees. As mentioned earlier, each node is a binary tree that has at most two children. They're called the left child and the right child. For example, each tree in figure 24-6 is a binary tree. In figure 24-6a, nodes B, C, D, and F are left children. The nodes C, E, and G are right children. The roots of the binary tree has two subtrees. The left subtree is rooted at B, and the right subtree is rooted at C. Thus, the left subtree of a binary tree is the left subtree and the root of its root, and likewise for the right subtree. Each subtree in the binary tree is also a binary tree. In fact, we can think of a binary tree recursively. So here are those figures that I was just mentioning from the last chart, but you can look over those and we'll continue our conversation. So for every subtree in a binary is also a binary tree. In fact, we can think of a binary tree recursively, as I just said. So full and complete binary trees, when a binary tree of height h has all of the leaves at level h and every non-leaf or parent has exactly two children, the tree is said to be full. Figure 24-6a shows a full binary tree. If all levels of a binary tree, but the last contain as many nodes as possible, the nodes on the last level are filled in from left to right, as in figure 24-6b. The tree is complete. The binary tree in figure 24-6c is neither full nor complete. In this case, a node can either have a left child but no right child, for example, node S, or a right child but no left child, for example, node U. Okay, what about balanced binary trees? When each node in a binary tree has two subtrees whose heights are exactly the same, the tree is said to be completely balanced. The only complete balanced binary tree are full. For example, the full tree in figure 24-6a is completely balanced. Other trees are said to be height balanced or simply balanced if the subtree of each node in the tree differs in the height by no more than one. A complete binary tree, such as the one in figure 24-6b, is height balanced, but so are some trees that are not complete, as figure 24-7 shows. Moreover, the concept of balance applies to all trees, not just binary trees. A node in a binary tree whose subtree differs in height by no more than one is known as a balanced node. Thus, all nodes in a balanced binary tree are balanced. So what about the height of a full or complete tree? In later chapters, the height of trees that are either full or complete will be important in our discussion of efficiency. 24-8 shows some full trees that get progressively taller. We can complete the number of nodes that each tree contains as a function of its height, beginning at the root of each tree in the figure. We see that the number of nodes at each level doubles as we move towards the leaves. The total number of nodes in the tallest tree in the figure is 1 + 2 + 4 + 8 + 16, or 31. In general, the node in a binary tree is anyway, we'll just talk about that in a little bit. So basically, you can start to figure that out here. It's in the textbook. It's a summation of all of those things that are the various levels. The number of nodes in a full binary tree is a function of the tree's height. And you can convince yourself that the result is true by examining figure 24.8. And you can prove it as an exercise by using mathematical induction. Okay, what about traversals of a tree? Until now, we treated the contents of the nodes in a tree simply as labels for identification because the tree is an ADT. However, its nodes contain data that we process. We now consider the nodes in this way. Traversing the items in the data collection is a common operation that we have seen in previous chapters. In those cases, data was arranged linearly so that the sequence of the items in the traversal was clear, such as not the case for a tree. In defining a traversal or iteration of a tree, we must process each node's data item exactly once. However, the order in which we visit nodes is not unique. We can choose an order suitably to our application because traversals of a binary tree are somewhat easier to understand than traversals of a general tree. We begin there. To simplify our discussion, we use the phrase, quote, visit a node to mean, quote, process the data within a node. We know that subtrees of the root of a binary tree are themselves binary trees. Using this recursive nature of a binary tree in the definition of its traversal is natural. To visit all the nodes in a binary tree, we must visit the root, visit all nodes in the root's left subtree, visit all the nodes in the root's right subtree. Visiting the nodes in the left subtree before visiting those in the right subtree is simply a convention, but we must follow it consistently through each traversal. When we visit the root before, between, or after visiting these two subtrees, however, defines three common orders for a traversal. The first traversal order uses a completely different approach. So in a pre-order traversal, we visit the root before we visit the root subtrees. We then visit all the nodes in the root's left subtree before we visit the node in the right subtree. In an in-order traversal, we visit the root of the binary tree between visiting the nodes in the root subtrees. In particular, it visit nodes in the following order. Visit all the nodes in the root left subtree, visit the root, visit the nodes in the right subtree. In a post-order traversal, visits the root of a binary tree after visiting the nodes in the root subtree. In particular, it visits the nodes in the following order. Visit all the nodes in the root's left subtree, visit all the nodes in the root's right subtree, visits the root. A level order traversal, the last traversal we will consider, begins in the root and visit nodes one level at a time. Within a level, it visits nodes from the left to right. Figure 24.12 numbers the nodes in a binary tree in the order in which a level order traversal visits them. So here in figure 24.9, the numbers of the nodes in a binary tree, the order in which the pre-order traversal visits them. After the first visiting the root, we visit the nodes in the root's left subtree. Since the subtree is a binary tree, visiting the nodes in pre-order means that we visit the root before visiting its left subtree. The traversal continues in this recursive manner until all the nodes are visited. Here, the numbers in the node in a binary tree, the order in which an in-order traversal visits them. Recursively visiting the nodes in the left subtree results in visiting the leftmost leaf first. We visit the leaf's parent next, and then the parent's right child. We visit the tree's root after we have visited all of the nodes in the root's left subtree. Finally, we visit the nodes in the root's right subtree in this recursive manner. So now doing things for post order. So in this figure, the numbers in the nodes in a binary tree in the reverse in the order in which a post order traversal visits them. We're recursively visiting the nodes in the left subtree results in visiting the leftmost leaf first. We then visit the leaf siblings and then the parent. After visiting all the nodes in the root's left subtree, we visit the nodes in the right subtree in this recursive manner. Finally, we visit the root. So here in a level order traversal, the last traversal we will consider begins in the root and visit the nodes one at a time with a level. Within a level, it visits the nodes from left to right. Figure 2412 numbers and nodes in a binary tree in the order in which the level traversal visits them. And I won't keep going through those details. And so you can see that the slightly different way that each one of these things is done. So a general tree has traversals that are in level order, pre-order, and post-order. An in-order traversal is not well defined for a general tree. A level order traversal visit nodes level by level, beginning at the root. This traversal is just like the level order traversal of a binary tree, except that the nodes in general tree can have more than 2 childs each. A pre-order traversal visits the root and then visits the nodes in each of the roots subtree. A post-order traversal first visits the nodes in each of the root subtrees and then visits the root last. So in figure 2413, it gives examples of pre-order traversal and a post-order traversal for a general tree. Let's talk about Java interfaces for trees. Trees come in many shapes and have varied applications. Writing one Java interface for an ADT tree that satisfies every use would be an unwieldy task. Instead, we write several interfaces that we can combine as needed for a particular application. We include these interfaces in a package that also will contain the classes that implement them. In this way, the package can contain implementation details such as a class of the nodes that we will want to hide from the tree's clients. The next chapter will examine these implementations. So let's talk about the interfaces for all trees. Fundamental operations, we begin with an interface that specifies operations common to all trees. The interface in listing 24.1 that we're showing here uses the generic type T as a type of data in the nodes of the tree. This interface is quite basic. It does not include operations to add or remove nodes, as even the specification of these operations depends on the kind of tree. We also did not include traversal operations in this interface since not every application uses them. Instead, we will provide a separate interface for traversals. Okay, for traversals, one way to traverse a tree is to use an iterator that has methods has next and next, as given in the interface java.util.iterator. As in previous chapters, we can define a method that returns such an iterator. Since we can have several kinds of traversals, a tree class could have several methods that each return a different kind of iterator. Listing 24.1 defines an interface for these methods. A tree class can implement this interface and define as many of the methods as are needed. For an interface for binary trees, many applications of trees, in fact, use binary trees. We could use a Java class of general trees for such an application, but using a special class of binary trees is more convenient and efficient. Because binary trees occur so frequently, developing special Java classes for them is worthwhile. We can define an interface for a basic binary tree by adding methods to those already in the interface, tree interface, and tree iterator interface. Since a Java interface can extend more than one interface, we can write the interface shown in listing 24.3 for a class of binary trees. And you can see the things that it's extending. So here's an example. Suppose that the class binary tree implements the interface binary tree interface. To construct the tree in figure 24.14, we first represent each of its leaves as one node tree. Notice that each node in this tree contains a one-letter string. Moving up the tree from its leaves, we use set tree to form larger and larger subtrees until we have the desired tree. So here are some Java statements that build the tree and then display some of its characteristics. And so we're showing that in this slide. Here's some more details. And so that's there available on the slide and also in the textbook. So here's some examples of some binary trees. We now look at some examples that use trees to organize data, leaving the details of the implementation for the next chapter. The first example includes a demonstration of some of the traversals introduced earlier in this chapter. For expression trees, we can use a binary tree to represent an algebraic expression whose operators are binary. Recall from segment 5.5 in chapter 5 that a binary operation has two operands. For example, we can represent the expression a divided by b as the binary tree in figure 2415a. And you can see that as we're showing it. The root of the tree contains the operator divide, and the root's children contains operands for the operator. Notice that the order of the children matches the order of the operands. Such a binary tree is called an expression tree. Figure 2415 also contains other examples of expression trees. Notice that any parentheses in an expression do not appear in trees. The tree, in fact, captures the order of the expression's operands without the need for parentheses. Okay, in terms of evaluating an algebraic expression, since an expression tree represents the order of expressions operations, we can use it to evaluate the expression. The root of an expression tree is always an operator whose operands are represented by the root, left, and right subtrees. If we can evaluate the sub-expressions that these subtrees represent, we can evaluate the entire expression. Notice that such is the case for each value, for each expression tree in figure 2415, if we know the value of the variables. A post-order traversal of an expression tree visits the root left subtree, then the right subtree, and finally the root. It takes if during the visits to the subtrees we evaluate their expression, we can combine the results with the operator in the root and get the value of the original expression. Thus, the value of the expression tree is given by the following recursive algorithm. You can see that on the slide here. Okay, what about decision trees? This is where we get into an example of expert systems. An expert systems helps its users solve problems or make decisions. Such a program can help you pick a major or apply for financial aid. It reaches a conclusion based upon your answers given to a series of questions. A decision tree can be the basis of an expert system. Each parent, that is a non-leaf, is a decision tree. In a decision tree is a question that has a finite number of responses. For example, we might use expressions whose answers are true or false, yes or no, or multiple choice. Each possible answer to the question corresponds to a child of that node. Each child might be an additional question or a conclusion. Nodes that are conclusions would have no children, and so they would be leaves. In general, a decision tree is any n-ary tree so that it can accommodate multiple choice questions. Often, however, a decision tree is a binary tree. For example, the decision tree in figure 2416 shows a part of a binary tree of yes or no questions that diagnose a problem with a television. To use this decision tree, we first would display the question in the root, which in the current node is the current node. According to the user's answer, we would move to the appropriate child, the new current node, and display its contents. Thus, we move along a path in a decision tree from the root to a leaf according to responses made by the user. At each non-leaf, we display a question. When we reach a leaf, we provide a conclusion. Notice that each node in a binary decision tree either has two children or is a leaf. What about a guessing game? Here's an example. In a guessing game, you think of something, and I have to guess what it is by asking some questions that have a yes or no answer. Suppose that a program asks the question for me. The program uses a binary decision tree that grows as the game progresses. Instead of creating the tree before it is used, the program acquires facts from the user and adds them to the decision tree. Thus, the program learns by playing the game and becomes more proficient over time. To simplify the problem, let's restrict your choices of things. For example, suppose that you think of a country. The program would begin with the simple 3-node tree pictured in figure 2417. With this new information, we augment the tree as in figure 2418. We replace the contents of the leaf that contained the wrong answer, Brazil, in this case, with a new question provided by the user. We then give the leaf 2 children. One child contains the guess that was in the former leaf, Brazil, and the other contains the user's answers, England, as a new guess. The program now can distinguish between Brazil and England. A decision tree provides operations that move us along a path through the tree and access the current node. Listing 24.4 that we're showing here contains a possible Java interface for a binary decision tree. And this is the second part. You can see this here in this chart if you want to look at that over in more detail or look that up in the text. For binary search trees, earlier chapters have already discussed the importance of searching for data. Since we can traverse the nodes in any tree, searching a tree for a specific piece of data is certainly feasible. Doing so, however, can be as inefficient as performing a sequential search of an array. A search tree, on the other hand, organizes its data so a search can be more efficient. In this chapter, we present the simplest kind of search tree, the binary search tree. Chapter 28 will look at other search trees. A binary search tree is a binary tree whose nodes contain comparable objects and are organized as follows. For each node in a binary search tree, the node's data is greater than all the data in the node's left subtree. The node data is less than all the data in the node's right subtree. For example, figure 2419 that we're showing here shows a binary search tree of names. As a string, Jared is greater than all the names in Jared's left subtree, but less than all the names in Jared's right subtree. These characteristics are true for every node in the tree, not only for the root. Notice that each of Jared's subtrees is itself a binary search tree. The previous definition of a binary search tree implies that the tree's entries are distinct. We have imposed this restriction to make our discussions simpler, but we could revise our definition to allow the duplicate entries. Chapter 26 considers this possibility. The configuration of a binary search tree is not unique. That is, we can form several different binary search trees from the same set of data. For example, 2420 shows 2 binary search trees containing the same names that are in figure 2419. Other binary search trees are possible. Okay, for searching a binary search tree, the organization of the nodes in a binary search tree enable us to search the tree for a particular data object given its search key. For example, suppose that we begin the tree in figure 2419 for the string Jim. Beginning at the root of the tree, we compare Jim and Jared. Since the string Jim is greater than the string Jared, we search the right subtree of the root, comparing Jim to Megan. We find that Jim is less than Megan. We search Megan's left subtree next and find Jim. To search for Laura, we would compare Laura with Jared, then with Megan, and then with Jim. Since Laura is greater than Jim, we would search Jim's right subtree, but the subtree is empty. So we conclude that Laura does not occur in the tree. We can express our search algorithm recursively. To search a binary tree, we search one of its 2 subtrees. The search ends when either we find the item we seek or we encounter an empty subtree. We can formulate the search by writing the following pseudocode, which we're showing in this chart. The algorithm is somewhat like a binary search of an array. Here we search one of 2 subtrees. A binary search searches one half of the array. You will see how to implement this algorithm in chapter 26. You think you could implement the ADT dictionary by using a binary search tree, you would be right. Chapter 26 will show how to do this. So what about the efficiency of a search? The algorithm best search examines nodes along a path through a binary search tree, beginning at the tree's root. The path ends at either the node that contains a desired object or some other node that is a leaf. In the previous segment, the search for gyms in figure 2419 examined the 3 nodes containing Jared, Megan, and Jim. In general, the number of comparisons that a successful search requires is the number of nodes along the path from the root to the node that contains a desired item. Searching for Jim in figure 2420A requires 4 comparisons. Searching 2420B for Jim requires 5 comparisons. Both trees in 2420 are taller than trees in figures 2419. As you can see, the height of a tree directly affects the length of the longest path from the root to a leaf, and hence affects the efficiency of a worst case search. Thus, searching a binary search tree of length h is big O notation h. Note that the tree in figure 2420b is as tall as a tree containing 7 nodes can be. A search of these trees has the performance of a sequential search of either a sorted array or a sorted linked chain. Each of these searches has an efficiency of big O notation n. To make searching a binary search tree as efficient as possible, the tree must be as short as possible. The tree in figure 2419 is full and is as short as possible binary search that we can form with this data. As you will see in chapter 26, inserting or deleting nodes can change the shape of the binary search tree. Thus, such operations can decrease the time efficiency of a search. Chapter 28 will show you strategies for maintaining the search's efficiency. Okay, for heaps, let's talk about definitions. A heap is a complete binary tree whose nodes contain comparable objects and are organized as follows. Each node contains an object that is no smaller or no larger than the object in its descendants. In a max heap, the objects in a node is greater than or equal to the objects in the node's descendants. In a min heap, the relationship is less than or equal to. And so we're showing that on the slide. Figure 2421 gives an example of max heap and a min heap. For simplicity, we use integers instead of objects in our illustration. For operations, in addition to typical ADT operations such as add, is empty, get size, and clear, a heap has operations that retrieve and remove the object in its root. This object is either the largest or smallest objects in the heap, depending on whether we have a max heap or min heap. This characteristic enables us to use a heap to implement the ADT priority queue, as you will see in the next segment. The Java interface in listing 24.5 specifies operations for a max heap. For priority queues, we can use a heap to implement the ADT priority queue, assuming that the class max heap implements max heap interface. A class that implements the priority queue as an adapter class begins as given in listing 24.6. Recall that we define priority queue interface in segment 719 of chapter 7. So here's an example of a general tree. Here's examples of general trees. We conclude this chapter with 2 examples of generic trees. A parse tree is useful in the construction of a compiler. A game tree is a generalization of a decision tree in figure 2417 and 2418. And we'll show a little bit of detail here, but you can also look into text. So a parse tree for an expression A times quantity B plus C is shown in figure 2422. Beginning at the tree's root, we see that expression is a term. A term is the product of 2 factors. The first factor is a variable, in particular A. The second factor is an expression enclosed in parentheses. The expression is a sum of 2 terms. Each of these terms is a factor. Each of those factors is a variable. The first variable is B, the second is C. Since we are able to form the parse tree, the string is A times the quantity, parentheses, B plus C, is a valid algebraic expression. For game trees, for a 2-person game such as tic-tac-toe, we can use a general tree to represent the possible moves in any situation. Such a decision tree is called a game tree. If a given node in the tree represents the state of the game after one player has made a move, the node's children represents the states possible after the second player makes a move. Figure 2423 shows a portion of the game tree for tic-tac-toe. Well, that's it for this chapter. We've covered a lot of material, but we'll call it an end of a lecture for now. Thank you.